Oh, fine. Fine. So now I'm trying to explain ANN architecture, multi-layer on ANN architecture with non-linear activation function. For explanation purpose, I took a small data where I want to predict a variable X. That means for a single variable, I'm going to predict that X may be a temperature or humidity, whatever it may be, based on the 3 input features. They are called as A, B, and C. Okay, that means I'm trying to predict only one variable. So you will get only one output from your ANN model. You will get only one output from your ANN model. That output you can call it as a O. O is called as predicted output by the ANN.
Sir, can you share this? Can you share the screen, sir?
Oh, sorry. Thank you, madam. Now it's okay, madam?
Yes, sir.
Fine. So I'm trying to explain artificial neural network, multi-layer artificial neural network with a non-linear activation function. For this explanation purpose, I took a small data set. In this data set, we are trying to predict a variable X. Only one variable we are trying to predict, that's the X, based on the 3 input features A, B, and C. Okay. So because we are trying to predict only one output variable, the output of your ANN model is only one output. That is the O. O is called as a predicted output by the ANN model. And we are trying to predict this output based on the 3 input features. They are called as the A, B, and C. So 3 input features. So we have to use the 3 inputs to our model. One is called A. We have to give one feature A, and we have to give the another feature, input feature, that is the B, and we have to give the another feature, that is the C. Okay. So A, B, C are the input features. Based on these input features, I want to predict the X or O. Fine. So as we have the 3 input features in our input layer, let's assume this is the input layer. I want to call it as a IP, input layer. Generally, we can call it as the ith layer, I. So because we have the 3 input, because we have the 3 input features, so we have to keep the 3 input neurons in the input layer, 3 neurons in the input layer. These neurons are called as the input neurons. So the number of neurons in the input layer is depending upon the number of input features in your data set. Fine. And coming to the last layer, so that is called as the last layer, that is called as the output layer. That is called as the output layer. And this output layer, we are trying to predict only one variable so that we have the only one output neuron. From that output neuron, we are going to get the predictions. So this is called as the OP layer or output layer. I want to call it as a kth layer. Now, in case of the multi-layer ANN, in addition to the input layer, in addition to the output layer, we have the hidden layer also. This middle part is called as the HL. I want to call it the HL, that is called the hidden layer. I want to represent this one with a J. J is called as the hidden layer. So hidden layer, so we have some neurons. The number of neurons in the input layer, number of neurons in the output layer are depending upon your data set and your approach. Whereas number of neurons in the hidden layer is a random. You have to tune it to get the better result. There is no thumb rule. These number of hidden neurons you have to keep in the hidden layer. There is no thumb rule. And here I'm explaining with single hidden layer. I'm explaining with a single hidden layer. And there is no need to keep only single hidden layer. You can go with multiple hidden layers also. What I'm trying to tell you is number of neurons in the input layer is based on your data set. Number of neurons in the output layer, that is based on your data set. Whereas number of neurons in the hidden layer is completely random. You have to tune it to get the until you got the better performance in terms of the errors or in terms of the accuracy. Second thing is, here I'm explaining the ANN model with a single hidden layer, but there is no need to restrict for only one hidden layer. You can go with the multiple hidden layers also. That's why it's called the deep learning or deep neural network. But I am explaining with only single hidden layer. The same thing will be happening for the multiple also. But taking the derivations, mathematical derivation becomes very complex if you go with more number of hidden layers. That's why I'm trying to explain with the single hidden layer. So randomly, I want to choose 5 neurons in the hidden layer. I want to choose the 5 neurons in the hidden layer. Okay. And all these neurons are fully connected. That means one input neuron should be connected to all of the hidden neurons. Should be connected to all of the hidden neurons. Same as this one also fully connected to all of the hidden neurons. And this one also connected to the every hidden neuron like this. This is called fully connected. Similarly, every hidden neuron should be connected to your output neuron like this. Then next. Now, previous case, we use only non-linear activation functions. Actually, as I said in the previous class also, most of the real-time problems, most of the practical problems, the relation between your output and input is a very, very high complex and highly non-linear. If you use the linear activation function, it may not work well. It may not work well. That's why you try to use the non-linear activation function. So I am trying to use the non-linear activation function, that is the S. S is called the sigmoid activation function. I want to keep in the both hidden layer and also in the output layer. Why I am using the sigmoid activation function? In order to build the non-linear relation between the inputs and outputs. Why? Because sigmoid is a non-linear activation function. So this is my architecture for this prediction. Okay. Now, so we will discuss about the algorithm and also we discuss about the required derivations. Okay. So first go to step number 1. Go to step number 1. Anyone can respond. What will be the first step in our training algorithm? Anyone please respond. What will be the first step in our training algorithm? We discussed it in the day 1, not day 1, day 2, day 3, we discussed it. That's why I'm asking you. So what will be the first step in the training algorithm, back propagation algorithm? Anyone, please? Or you can use the chat box also. Anyone? So what will the first step? Right. Thank you, Mrinalini. So first we are going to read the data. Good. So we are trying to read the data first. So first step is read data. From the data set, we have the data set A, B, C input features and also output feature. Good. So after that, what will be the next step? Anyone? What will be the next step? Intama, what will be the next step? Anyone, please? Fine. Otherwise, I will move further. So next step will be, that means not next step, within the step, we need to read the data A, B, C, X and also randomly initialize all model parameters. Random initialize all model parameters. What are the model parameters? What are the, very good, learning rate, right, very good. Chintam Ronalni, right, learning rate initialization and weights initialization, perfect. So random weights initialization, coming to the weights initialization. So actually we have the weights like W11, W12, W13, W14, W15. Similarly here W31, W32. So W31, W32, W33, W34, like that. These all are the weights between the input layer to the hidden layer. So these weights, I want to call these weights as a Wij. So Wij is a weight matrix between the input layer and hidden layer. This will be like this: W11, W12, W13, W14, W15. Similarly, W21, W22, W23, W24, W25. Into the W31, W32, W33, W34, and W35. So what is the shape of this weight matrix between the input layer and hidden layer? You can understand my pronunciation. Input layer and hidden layer. So the shape is 3 cross 5. Y3 because input layer neurons are 3 and Y5 hidden layer neurons are 5. That's why it's the 3 cross 5. Similarly, you have the weights between the hidden layer and output layer also. It can call it as a W11, W21, W31, W41, W51. Like WJK, this is called as the weights between the hidden layer J and output layer K. So WJK can be represented as W11, W12, W21, W31, W41, W51. This is my weight matrix. So you need to random initialize the model parameters. What are the model parameters? Nothing but the weights. Wij, Wjk. So in addition to the weights, what else you have in a ANN model? I told in the third day. In addition to the weight, and a few more model parameters also exist. And those parameters are called as weight parameters. Okay, sorry, bias parameter. So how many bias parameters have? Every layer except input layer, you have the bias parameters. That means in hidden layer, you have the bias parameter. In output layer also, you have the bias parameter. Number of bias parameters is depending upon the number of neurons in that particular layer. The number of neurons in the output layer equal to only 1. So you have the only one bias parameter. You have the only one bias parameter. For every bias parameter, input is 1. Every bias parameter, input is 1. And similarly, how many number of neurons are in the hidden layer? We have the total 5 neurons in the hidden layer. So you have 5 neurons in the hidden layer. So you have the 5 bias parameters, right? You have the 5 bias parameter. So this may be the bias parameter 1, and this will be the bias parameter 2, and this will be the bias parameter 3, and this will be the bias parameter 4, and this will be the bias parameter 5. For all the bias parameter, input equal to 1. So this B1, B2, B3, B4, B5, all these parameters, I want to represent that one as a BJ. BJ is nothing but the bias parameters in the hidden layer B1, B2, B3, B4, and B5. So you need to random initialize weight matrix of both input to hidden, hidden to output, and also bias parameters of the hidden layer and bias parameters of the output layer. You have to randomly initialize. In addition to that, as the mononally said, you need to initialize your learning rate. I want to keep it as the learning rate as a 0.1. And also you have to initialize number of epochs. Number of epochs equal to 100. Right? So this is our first step, right? Now, what will be the second step? So what will be the second step? So second step, we can call it as the iterative algorithm. You can set iteration equal to 1. And step number 3, I want to use the stochastic gradient optimizer. You have to take the sample by sample. Take the first sample, take the second sample like that. So you can call sample equal to 1. And what is the step number 4? Anyone now? Now tell me what will be the step number 4? Anyone? So we are reading the data, initialize the iteration, initialize the sample also. What may be the next step? So what will be the next step? After initialization, iteration, setup, and a sample setup, what will be the next step? So even if you're not attending the session for the past 4 days because of your busy schedule, but at least if you open the recordings that I shared, then you are in a position to give the answer to my question. What will be the step number 4? So step number 4 is prediction calculations, forward pass. Step number 4 is forward pass. Forward pass means so calculation of the predictions. So how we calculate the prediction? So if you want to calculate the predictions, first you need to calculate the net input to the your net input. That means here available input to the hidden layer. I can call it as a net J. Net J is nothing but the net input to the hidden layer. So you have to calculate that part. So net J equal to, how we can calculate the net input to the hidden layer? Tell me. So network is available now. How we can calculate the net input to the hidden layer? So net input to the hidden layer is calculated based on your inputs A, B, C and your weights between the input and hidden layer. So net input to the hidden layer J equal to, I can call it as a Wij weight matrix multiplied by my input matrix A, B, C. In addition to that, you have the bias parameters also. For every bias parameter, you have the input 1. So that is your bias parameter Bj multiplied by 1. That's called Bj only. That is the net input to your hidden layer. Now tell me, after calculating the net input to the hidden layer, what will be the output of the hidden layer? This is the input. What will be the output? In between, you have the sigmoid activation function. So what will be the output? Oj. What is the output Oj? So output of the hidden layer Oj equal to, because I am using the sigmoid activation function, so that's why it's the 1 by 1 plus e power minus net input to the hidden layer. This is how we can calculate the output of the hidden layer. Right? Next, once you got the output value, next you have to calculate the net input to the output layer. So net input to the output layer can be called as net k. Net input to the output layer is a net k. So how we can calculate that net k? That is depending upon the output coming from the hidden layer multiplied by weight and add your bias parameter. That means you can write Wjk into output from the hidden layer Oj plus your bias parameter Bk. After that, you need to calculate the output. Output of the output layer, nothing but the prediction. You can call it as OK. Output of the output layer or prediction. So how we can get that one? So OK equal to, as I am using the segment activation function in the output layer, so you can use the linear activation function also. Okay. So here I am using the segment activation function. So OK equal to 1 by 1 plus e power minus net k. So this is how we are calculating the output. Okay. So from this forward pass, we are going to calculate the net output of the hidden layer and final output of the neural ANN. We have to calculate. That is called as the forward pass. Okay. Now we will move further. So what will be the next step? Step number 5. So step number 5. So that is the. So step number 5. That is the backward pass. So that is the backward pass. In the backward pass, we have to update the weights. What I want to tell you is, in the forward pass, this is called as the forward pass. So in the forward pass, we are calculating the predictions. Okay. And whereas in the backward pass, so we are calculating the delta W and delta B, that means change in weights and change in bias parameters. And later we are updating the weights and bias parameters. Okay. So that is the backward path. That's why it's called the back propagation algorithm. Your error will be propagated back. So it's called a back propagation algorithm. Now back propagation algorithm, it is a combination of both forward pass and also backward pass. Okay, the combination of both is a back propagation algorithm. Now in the backward pass, so as I said, we need to calculate the delta W for the input and hidden layer and hidden and output layer, delta B for the hidden layer and also for the output layer. Now we have to work on this derivation part. Now we need to work on this derivation part. Okay. So first, I think if you are following from the first step, if you are following from the initial day, first day of this FDP, then you are able to understand. You are able to in a position to give the answers. So if you want to calculate the delta Wij, no, first I will calculate delta Wjk. That means I want to calculate the change in weights between the your jth layer and kth layer, hidden layer and output layer. So if you want delta Wjk, what is the expression as per the gradient descent algorithm? That is the minus eta into your error function dou E by dou Wjk. But you have a doubt. What is the E value? I think most of the people who are following that, they know your error function E equal to 1 by 2 into your desired output dk minus your predicted output OK whole square. This is called as the error that we are using. It's called as the mean square error that we are using for the ANN, artificial neural network. So based on this expression, we are going to calculate the delta Wjk. Now, delta Wjk equal to minus eta into dou E by dou WJK, right? I want to find in E, I have a OK. So I want to write dou E by dou OK. In OK, I have the net K. So I can write it as a dou OK by dou net K. Dou OK by dou net K. And in net K, I have the WJK expression. So I want to write this one as a dou net K by dou WJK. So you can see both are same, right? This OK cancel, net K cancel, then you have the dou E by dou WJK only. It is called as splitting the partial fractions. Partial differentiation splitting. I'm splitting the partial differentiation here. So then what happened? So I want to write this expression again. So delta WJK equal to minus eta dou E by dou K. What is the dou E by dou K? What is the differentiation of E with respect to OK? These two come forward, two cancel. So you have the dk minus OK. In addition to that, OK coefficient is -1. So this minus plus becomes plus. This is completed. Now, what is the dou OK by dou net K? Dou OK by dou net K. It is a sigmoid activation function. So as I said, for a sigmoid OK is a sigmoid activation function, right? So for a sigmoid activation function, what is the derivative? So I told this also previously. If f of x is a sigmoid activation function, what is the f dash of x? Anyone, please? If f of x is a sigmoid activation function, what is the f dash of x? Nothing but the dou f by dou x. If f of x is a sigmoid activation function, what is the dou f by dou x? Nothing but the derivative of the first order derivative of the your softmax function. Sorry, sigmoid function. If f of x is a sigmoid activation function, what is the f dash of x? The same question is given in the quiz examination also. Okay. So f dash of x equal to f of x into 1 minus f of x, right? So as per this concept, so if OK is a sigmoid activation function, what is the dou OK by dou net K? So that is the OK into 1 minus OK. And dou net K by dou WJK. Net K we have, if you differentiate this net K with the WJK, what is the outcome of this differentiation? So that is called as the OJ. So this is the delta WJK expression. Delta WJK expression. Okay. Now delta WJK is over, right? Now I want to work with delta BK. Delta BK means change in bias parameter in the output layer. Change in bias parameter in the output layer. Okay. So delta BK equal to, how we can calculate delta BK? That is the minus eta into dou E by dou BK. So that can be further splitting as minus eta into dou E by dou OK, dou OK by dou net K, and dou net K by dou BK. Then both are same, right? From this expansion, delta BK can be written as minus eta dou E by dou OK from here. That is the dk minus OK, it becomes plus. Dou OK by dou net K from here. So that's the sigmoid. So OK into 1 minus OK. And dou net K by dou BK here. Dou net K by dou BK. The coefficient will be 1. So this is our delta BK expression. This is our delta BK expression. You have to remember all the things while writing the coding. When I'm writing the coding. So now delta WJK completed and delta BK also completed. Now I want to work with delta Wij. I want to work with delta Wij. That means change in weights between the input layer to the hidden layer. Change in weight between the input layer to the hidden layer. So that's equal to minus eta dou E by dou Wij. So we can expand, we have to split this differentiation like minus eta into dou E by dou OK, because in the error function you have the OK expression. In OK you have the net K. So dou OK by dou net K. And in the net K you have the OJ. So dou net k by dou oj, and in oj you have the net j. So dou oj by dou net j, and in net j, if observe in net j you have the wij. So you can write dou net j by dou wij. So if you expand like this, then you have the delta wij equal to minus eta dou e by dou ok already we completed. That is the dk minus ok, and this will become the plus. What about the dou ok by dou net k? That also completed. Ok into 1 minus ok. And what is the dou net k by dou oj? Dou net k by dou oj. That is called as wij. Now, what is the dou oj by dou net j? Dou oj by dou net j. It is a sigmoid activation function. So you have the oj into 1 minus oj. And finally, we have the dou net j by dou wij. Dou net j by dou wij, you have the ABC inputs. So you have the ABC inputs. So this is the delta wij. Delta wij. Okay. So finally, this is your delta wij expression. You have to use this expression also. And one more thing we require, that is called as the delta bj. So if you want the delta bj, same like this, minus eta into dou e by dou bj. That's equal to minus eta into dou e by dou ok, dou ok by dou net k by dou oj, and dou oj by dou net j, and dou net j by dou wij. So from here, delta bj equal to what happened? Minus eta dou e by dou ok. This expression, right? So it will become a plus dk minus ok. Dou ok by dou net k, this expression. Ok into 1 minus ok. Dou net k by dou oj. Dou net k by dou oj. That is the wij. wij. And dou oj by dou net j, this expression. oj into 1 minus oj. And finally, dou net j by, sorry, no one corrected me. I am trying to calculate the delta bj. If it is a delta bj, then this differentiation should be with respect to dbj. So what is the net j? Dou net j by dou bj. Dou net j and differentiate with bj, then the output will be only 1. 1 means into 1, that's it, into 1. So this is our final expression for the delta bj. Done. This is how we have to, that the error will be propagated. This is how the what's called weights are updated. Okay. Now I want to use all these delta W expressions in the backward pass. I want to use all the things in the backward pass. So in the backward pass, what we have to do? Calculate the delta Wij and calculate the delta Wjk, calculate the delta Bj, calculate the delta Bk. So delta Wjk can be written as the eta into dk minus ok into 1 minus ok into oj. And the delta Wij can be written as eta into dk minus ok into 1 minus ok into wjk. Sorry, you have to correct it, please. In the delta Wij, this Wij is coming from dou ok by dou net k. Dou ok, not dou ok, but dou net k by dou oj. What the dou net k by dou oj? If you differentiate net k with respect to oj, your expression will be wjk. So this will be not Wij. This is the wjk. Similarly, here also same. It's also not w ij, it is a wjk. So here also you can use the same. So wjk into oj into 1 minus oj into your input parameters a, b, and c. And delta bj equal to eta into dk minus ok into ok into 1 minus ok wjk oj. That's it. No, no, not OJ. OJ into 1 minus OJ. Whereas delta BK equal to eta into DK minus OK into 1 minus OK. This is how we are calculating in the backward pass. That's how we are calculating the delta W and delta B. And next step number 6 is you have to update the weights. Like update the weights means you have to update Wij equal to Wij initial weight plus delta Wij. Similarly, update the Wjk, weights between the hidden and output layer. Wjk plus delta Wjk. And similarly, update the bias parameter of the hidden layer, bias parameter of the output layer. That is the Bj plus delta Bj, Bk plus delta Bk. We have to do that part also. Okay. And finally, step number 7. Step number 7. So what is step number 7? Weights updated, bias parameters are updated. Now you are going to update your sample. Sample equal to sample plus 1. Now step number 8, all the things we discussed in the previous class. Step number 8, if you have to check whether all the samples covered in the training data. NS means number of samples in the training data. If your current sample number is greater than the number of samples in the training data, it is a true, then you have to move to the next step. If it is a false, then you have to move to step number 4, I think. Yeah, step number 4. You have to move to the step number 4. That is the forward pass. You have to move. We discussed all the things. So step number 9. Now next step means update the iteration. So iter equal to iter plus 1. Iter equal to iter plus 1. And step number 10 is check the convergence. That means if the current iteration value is greater than number of epochs that you mentioned at the time of the initialization. If you said epochs equal to 100, your algorithm should run in the 100 epochs only. So if it is a true, go to next step. And if it is a false, go to step number 3, where you have to again start from the first sample. That means you are starting the new iteration. Okay. Finally, step number 11 is, so you have to save model. ANN model save. You have to save the model. So that means you have to save your Wij weights, Wjk weight, Bj weight, and Bk weight, and calculate training error and also testing error. If the training error and testing error are small and you yourself and your client also happy, then directly deploy your model. Okay, deploy your model. Okay, finally there is a deploy your model and you can stop. So this is the complete process of a back propagation algorithm of a ANN model, multi-layer ANN model with a nonlinear activation function. The derivation slightly, the expressions of delta W, delta B will be changes from one activation function to the another activation function. That you have to remember. I explained the derivation for the sigmoid activation function, but that will be changes from the one activation function to the another activation function. So I think you are clear with this complete algorithm, I think. Okay. Now, firstly, I will move to draw the flow chart. Later, I will move to the programming part. I will draw the flow chart. So start. And here you have to read data and randomly initialize your weights and the bias parameters. You have to randomly initialize the weights and bias parameters. After that, you have to set your learning rate value something, and you have to set number of epochs equal to some 100 like this. So this is our first step. So next step is, we discussed earlier, we have to go for the forward pass. So forward pass means for the forward pass. So calculate the net j, that is the net j means Wij into Wij into your inputs A, B, C plus your bias Bj. Later calculate the Oj. Oj equal to 1 by 1 plus e power minus net j. Let us calculate the net k. Net k means the net input to your output layer. That is the wjk into oj plus bk. And later you have to calculate the output. OK equal to 1 by 1 plus e power minus net k as I am using the segment activation function. These 4 steps you have to include in the forward pass. And next step is you have to calculate the change in weights. You have to calculate the change in weights. Change in weights means delta w ij equal to eta into dk minus ok into ok into 1 minus ok into wjk, right? And that's it, no? Maybe I forget. Yeah, wjk, right? Huh? Wjk into oj into 1 minus oj multiplied by your inputs A, B, C. Similarly, you can calculate the delta wjk, that's equal to eta into dk minus ok into 1 minus ok, okay, into oj. And similarly, you can calculate the delta bj, and also you have to calculate the delta bk, the expressions we already discussed here, derived and discussed. So delta bj expression and delta bk expression. So you have to incorporate, you have to calculate the delta wbj, delta bk, delta wij, delta wjk. After that, you have to update your weights and bias parameter like w equal to w plus delta w. W includes wij and wjk both. B equal to b plus delta b. So b includes, so w includes wij and wjk, and b includes bj and bk both. Simplify, I'm writing like. So after that, what you have to do? You have to update your sample number. So sample equal to sample plus 1. And you have to check for the convergence criteria. If the sample number is greater than your number of samples in the training data. If it is no, where to go? We already discussed it. If it is yes, you have to move to the next step. Okay. What is the next step here? What is the next step? Next step is iter equal to iter plus 1. You have to update your iterations. And later you have to check for the convergence criteria. Convergence criteria means is the current iteration value greater than epochs or not. If it is greater than number of epochs, then if it is S, then you have to algorithm is completed. So simply save model, calculate errors, and deploy. So at the stop. So if it is not exist, if it is no, where to go? Again, we have to start from the first sample. Again, we have to start from the first sample. So again, include one line you have to include here. We are in the sample 1. Take the first sample and do the forward pass. So go to sample, first sample. Okay. And next, if it is a sample count is not greater than number of samples in the training data, so then you have to go for the predictions again, forward pass. That's it. So there is the 2 for loops in your code. One is for the samples, another for loop is for the iterations. So this is our complete flow chart of a back propagation algorithm for a ANN, multi-layer ANN with nonlinear activation functions. I think it's clear now. Now we will move to its implementation using the Python from the scratch. After that, we will take a break and we will discuss about the ANN for the clustering, and we will discuss about the code also. Fine. Now I will move to the coding part. So most of the steps are repeated. So what are the code we discussed in the second day and third day? Most of the code is repeated with small changes. Okay. The participants who are following from the day 1, they're able to understand. or the participants who are seeing the videos up to date, they are also able to understand what I'm saying. If not, so once again, in your free time, go to old videos and then you can learn again. So coming to our data set. So, but the thing is, I think drive is not mounted. Yeah, drive already mounted. So this data is available in my Google Drive with the name of sample data for XLX. So in this Excel file, I have this data. I want to read this data, which is available in this Excel sheet, and I want to attach to a variable called data. I want to read the data from this Excel and store it in the data. For that one, I'm trying to run this cell. So that's it. So we are getting the complete data. That complete data is coming here. So as usual, after importing the data, our next step is we are going to split the data. So split the data means we have whatever the data we have, or the complete data, we have to fit some part of data for the training purpose, and we have to use remaining part of the data for the testing purpose. But the splitting of the data is done randomly and row wise. Row wise means maybe this row go for the training, and remaining 2 rows go for the testing, or 0th row, 1st row, 3rd row, 4th row are going for the training, and 2nd row going for the testing. So it's randomly taken in a code. So for the data split, we have a method called train_test_split. For this method, you have to pass your original data, this one. Test size means 0.05 means 5% of data will be going for the testing, and remaining 95% of data going for the training. So some questions are given already in the quiz like this. So check once, nothing will be happening if you attempt the quiz, but still only 1 or 2 participants are attempted the quiz. I don't know why remaining. So it's better to learn something and try to attempt the quizzes. You are able to, if you listen the videos, at least if you listen the class. So what happened is this train test split method will split this original data for the training purpose and also for the testing purpose. So data underscore training has the training data, data underscore test has the test data. So this I am trying to split the data. After data splitting, next step is where you only told. Next step is after data splitting, next step is initialize. So random initialize the weights and bias parameters. I'm randomly initializing the weights and bias parameters. That also we discussed it. Why I'm using the np.random.uniform for the random initialization. -1 and +1 are the lower limit and upper limit. You can choose any limits. And why I'm taking the 3 and why I'm taking the 5, you only told earlier. That is, my Wij size is 3 rows and 5 columns. That's why 3, 5. My Wjk is 5 rows and 1 column. That's why it is a 5, 1. My Bj is 5 row and 1 column. That's why it is a 5, 1. Whereas my Bk is only 1 value. That's why it's a 1, 1. So we are randomly initializing all these parameters. So after random initialization, what will be the next step? Forward pass. Okay. So our next step is forward pass. This one. Next step is forward pass means you have to calculate the net J. How we calculate the net J? I will open the forward pass code also. We have to calculate the net J. How we calculate the net J? So net J equal to Wij into inputs. This is the Wij into inputs. You may have a doubt. Why sir 0:3 inputs? Because if you observe our data, we have the 4 rows. Out of 4 rows, first 3 rows are the inputs. A, B, C are the inputs. So this is called as the 0 index. This is called as the index 1. This is called as the index 2. This is called as the index 3. That's why we are including 0:3. Index 0, index 1, index 2. 3 columns. In Python, that stop limit or endpoint is excluded. 3 will not be counted. 0, 1, and 2. 3 columns only taken. And those 3 columns A, B, C multiplied with Wij, A, B, C are multiplied with Wij, and plus add your bias parameter Bj, that will give the net J value. Once you got the net J value, calculate the Oj. So Oj equal to 1 by 1 plus e power minus net j. 1 by 1 plus e power. NP dot exponential means the Python for exponential, we have to use the NP dot exponential. That means e power minus net j. And net k equal to wjk into oj plus bk. Net k equal to wjk into oj plus bk. OK equal to 1 by 1 plus exponential of minus net k. That's how we can calculate our predictions, OJ and OK. That means OJ means output of the hidden layer and OK means output of the output layer. We have to calculate like this. So this complete part I am including in a function called forward pass. So in future, if I want to do the predictions, I will use the forward pass function. I will not write all these 4 lines of code. I will use only forward pass function. Similarly, coming to the backward pass. So in case of the backward pass, what we have to do? The backward pass, we have to calculate the delta wij, delta wjk, delta bj, delta bk. That's what I included here. Delta wjk, how we calculate the delta wjk? Delta wjk equal to eta, that is the learning rate. This is the learning rate multiplied by dk minus ok. dk means desired output. So where desired output is available? Where desired output is available in the last column. Last column is what is the index? Index 3. So that's why I'm taking the index 3. That means this is called as your desired output. These are your desired output minus desired output minus OK. So that's why OK. Again, OK into 1 minus OK. OK into 1 minus OK. And multiplied with, I want to calculate the delta wjk, multiplied with oj, multiply with oj. That is called as the delta wjk. Once you got the delta wjk, you can easily update your wjk. Wjk equal to wjk plus delta wjk. That's what I included. Wjk equal to wjk plus delta wjk. Okay. And later, delta bk. How we calculate delta bk? Delta b equal to eta minus desired output minus predicted output into 1 minus predicted output. So that's what here. Eta into desired output. That means fourth column with index 3. dk minus ok into 1 minus ok. So that is your delta bk. And after that, try to calculate the delta wij and delta wjk. Sorry, delta wij and delta bj. These two parts, delta wij and delta bj, we need to calculate. So delta wij equal to, so we know already, delta wij equal to eta into dk minus ok, eta learning rate. This is the d minus o, ok into 1 minus ok, wjk, wjk, oj into 1 minus oj, oj into 1 minus oj, and your inputs. You have a doubt. Where is the ABC? Here 0, column 3. Index 0, index 1, index 2. Index 0 means A, index 2 means B, index 1 means, index 0 means A, index 1 means B, index 2 means C. So the 3 values will be comes into here. Right? Similarly, delta bk equal to eta into dk minus ok, delta bj equal to eta into dk minus ok, eta into learning rate, desired output last column, output ok into 1 minus ok into wjk into oj into 1 minus oj into 1 minus oj. So this is how later we have to calculate wij equal to wij plus delta wij, bj equal to bj plus delta bj. This is called as your backward pass. In the backward pass, we are going to update the weights. We're going to update the weights and the bias parameter. Update the weights and the bias parameters. Whereas in the forward pass, we are calculating the outputs, OJ and OK. So this also completed. Now run the training algorithm. So what is the training algorithm? Learning rate, I want to keep it as a 0.1. And epochs, I want to keep it as epochs equal to 100. So outer for loop should be epochs, iterations that you have to keep. And why I'm using the Q1 here? Anyone at least who are following, they are able to give the answer. Why I'm using the Q1 here? And I will go to your back code for the Q1. This is the Q1 code. This is the Q2 code. Clearly observe Q1 equal to length of data train. Q2 means length of data test. Now my question is, why I am including Q1 not Q2? Anyone please? Why I am including Q1 not Q2? Anyone please? In the training algorithm, I am using the Q1 not Q2. What is the reason? Any reason why I am using the Q1 in the training, not Q2? The participants who are following, because I already explained in the day 2 and day 3 also. That's why I'm asking. Okay. Here I'm choosing the Q1 because we will use the training data samples to update the model parameters, not testing data samples. Test data samples used to test the model. Training samples are used to update the weights. So Q1, that's fine. So inside the loops, if you observe our code, inside the loops, if you observe our code, what we have to call? We have to call our forward pass function, and also we have to call our backward pass function. That's what I'm doing here. I'm calling the forward pass function and I'm calling the backward pass function. And for these functions, the code is already written in the previous cells. So just simply run this algorithm. Forward pass and backward pass. If you observe, so these are my initial weights, and later the weights are updated like this. After training, the weights are updated. So that means the back propagation algorithm is this one. But inside forward pass, these are the 4 lines executed, and inside the backward pass, so these lines are executed. I call them as a functions. Otherwise, you have to write the complete code here. In these 2 lines, in place of these 2 lines, you have to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 lines of code you have to write here to train the model. So as usual, once the training was completed, you have to find the predictions on the testing data. So predictions are nothing but we have to use only forward pass. As I said, right, we have the forward pass function, we have the backward pass function. Backward pass function is used to update the weights and bias parameters, which is used in the training algorithm. That's why I used it here in the training algorithm. Whereas in case of the predictions, we are going to predict the output only. If you want to predict the output only, this forward pass function is sufficient. This forward pass function is sufficient, right? So that's why just I am calling this forward pass function here. Just call this forward pass function. So in the forward function, I want to do the predictions with the testing data. So test data is available with variable called data underscore test. You can see here. Data underscore test has the test data. Data underscore train has the train data. Okay. So that's why just I'm calling the data underscore test data I'm passing. Now it will give the both OJ and OK. Your forward pass will give the OJ and OK, right? Your forward pass will give the OJ and OK. But when it comes to the predictions, we need the predictions of an ANN model, predictions of an output layer, predictions of an output neuron. So predictions of output layer or predictions of output neuron nothing but OK. OK is where the OK is placed. OK is placed in the second part, right? That's why I am keeping the second part only. In the first part, just keep underscore because I don't want to take that OJ values. I don't want OJ values. Simply, I kept the underscore and I want the OK values, and the OK values I want to store in this array. That's why I kept here. Okay. Similarly, you can do the predictions with the training data also. Similarly, you can go with predictions of the training data. Go with prediction the training data. So training data, that's why I'm taking the Q1. Here it's the testing data, that's why it's the Q2. Again, it's the predictions, only take the forward pass. And because prediction nothing but the prediction available at the output neuron, output layer, that's why you have to keep only the second part, first part should be underscore. Because first part is the OJ, output of the relay, that's not required at the time of the prediction of test data. So simply run this shell, then all the predictions with the training data stored in preditrain, all the predictions on the test data stored in the preditest, and actual output will be available in the data test fourth column, the third index. Actual values of a training data are available in the data underscore train in the fourth column with an index of 3. Error computation, simply error computation. So this is the error computation. So mean square error equal to Y3 here, index 3 means fourth column. Fourth column is the output column. That's why index 3 I am taking. So data test and data train have the actual output values. Preditest is the prediction value by the ANN on the test data. Preditrain is the prediction of the output with the training data. And we are comparing the predictions with the actual on test data and also train data. So now find the mean square error. So see, my mean square error is almost 0, 10 to the power of minus 5, 10 to the power of minus 5, almost 0. So I am happy with the errors and my client also happy. So directly deploy the model. Now deploy the model is nothing but the deploying of a model is nothing but what? So deploying of a model is nothing but what meant by deploying of a model? So deploying of a model is nothing but the keeping the or using the updated weights and the bias parameters of a trained ANN model in the backend of the application. Use the updated weights and update the bias parameters in the backend of the application. That's it. So I am using the updated weights and I am using the updated bias parameters in the backend of an application. Here, what the application is, this application will ask the user enter the value of A, enter the value of B, and enter the value of C. And all these three values are stored in the input vector. And this vector is passing to your forward pass function. The forward pass function will give the prediction. That prediction is nothing but your ANN prediction. So enter what value I had to enter. Otherwise, we can take any one sample from our data. I want to take 0.1, 0.2, and 0.3. I'm expecting 0.85. This is my data, right? Already we know the answers also. So if you enter the 0.1 as a, if you enter the 0.2 as a B, if you enter the 0.3 as a C, then the output will be 0.85. So you can check here. So 0.1, 0.2, 0.3. I'm expecting 0.85. That's it. We are getting the output value 0.85. How we are getting? Because the ANN model already trained. And the trained weights and bias parameters I used. And based on this trained weights and the bias parameters, whenever giving the input, it will predict the corresponding output. So we are getting the prediction more close to your actual values also. That's happy. That's what we are expecting, right? We are expecting from ANN model, the prediction should be more close to the actual values. Prediction should be more close to your actual values. Understood, right? So this is the implementation from the scratch using Python for an ANN with a sigmoid activation function. For ANN with sigmoid activation function. Okay. Now, next we will discuss about the small application. So I want to demonstrate load forecasting application on a substation. Electrical substation. So if you are a CSC people, don't worry anything. You can see this one as a numbers, that's it. If I say it is a load forecasting, I will use the load values in terms of numbers. If I'm working on a temperature prediction, I will use the temperature values in terms of numbers. If I'm trying to work on humidity prediction, I will use the humidity value in terms of the numbers. Right? So this it is numbers only. It is irrespective of the department. Everyone, mechanical also finally it's the numbers. Only that the background will be changed. But finally we are getting the numbers only. With that numbers only we will use for the predictions. So actually, this is my project done by my students in 2018 actually. No, 2019. This CSV file has the actual load values, electric power load values on a 33 by 11 kV substation in our Warangal. The practical data collected. And that practical data we stored in our Google Drive. So that data I want to read from the CSV file and stored with a variable data. Stored with a variable data. Okay. Now, so that's completed. Now I want to find that means the total data that we collected is a 4-month duration, I think. September, October, November, and December. 4 months data. It's available. So 4 months hourly data. 4 months hourly data means so September, I think 30, October 31, and November 30, December 31. So 2 and 4, 3 is 12 into 24. Because it's a total number of days, and every day we have the 24 hours. So 122 into 24. So what is the value? 2981. Maybe some days I think missed it. So the size of this data may be 2184 actually. The total data values are 2184. 2184 total data. The hourly data we collected for that period. Okay. Now I want to read this data and I want to identify what is the minimum load and what is the maximum load I want to calculate. So minimum load I want to calculate, maximum load I want to calculate. If you want to calculate the minimum value in the data, you can use data.min. If you want to find the maximum value in the data, just use the data.max. Just simply run this cell. That's it. So in my complete load data, minimum load is 3,377 kilowatts and maximum load is 8,841 kilowatts on that substation over that period. So this is my load actually. Top 5 samples of the load. Now, because these are the very huge numbers, in order to make my computation fast, I want to normalize this data. So normalize this data is nothing but we have scaled down this data in the range of 0 to 1. Scale down the data in the range of 0 to 1. How we scale down the data? Where it is? Scale down the data in the range of 0 to 1. How we scale down? So let's assume I have the load values, right? Let's assume load values are 200, 100, 300, 400, let's assume. And how we normalize this data? How we scale down the data between the 0 and 1? First, you have to identify the minimum load. What is the minimum load? 100. Later, identify the maximum load. That maximum load is 400. Okay. Minimum load is 400. Now, normalization formula is actual load value minus minimum value divided by maximum value minus minimum value. Okay. So what is the actual value? 200 minus what is the minimum value? 100. What is the maximum value? 400. What is the minimum value? 100. So value is 200 minus 100, 100. 400 minus 100, 300. It is a 1 by 3, nothing but 0.3. That's how we have scaled down the values. And this is a 100, right? How we can normalize this part? So x value, that means actual value is 100. Minimum value 100. Maximum value 400. Minimum value 100 is equal to 0. And coming to this part, so actual value 300. Minimum value 100. Maximum value 400 minus 100 is equal to how much we are getting? 300 minus 100, 200. This is a 300. So it is a 0.6. Similarly, 400. X value is the 400. Minimum value is 100. Maximum value is the 400. Minimum value is 100 is equal to 1. See, if it is a 200, after normalization it is 0.3. If it is a 100, after normalization it is 0. If it is 300, after normalization it is 0.6. If it is a 400, after normalization it is 1. Like that we are scaled down. So this is what I am doing manually. But if you have the huge data, 2184, we can't do it manually. That's why I'm writing a code. So in Python, we have a library or method, in sklearn library, we have a function or method called min-max scalar. And with this min-max scalar, we can scale down our actual values into the 0 to 1 range. You can scroll down actual values into the 0 to 1 range. Okay. So this is the piece of code. We can use it. You have to call the function and create an object for that method. And you have to use that object ms.fitTransform, pass your original data. Then what happened? It will be transformed into your normalized value. You can see actually you have 551, but now it becomes a 0.39. It is a 4983, it becomes a 0.2938. Okay, so this is how we can normalize the data. This is called as the normalization. So actual values are converted in the range of 0 to 1. Converted into the range of 0 to 1. Okay. Now, I want to go with small data pre-processing. So what approach we followed in that project is, we are trying to forecast the load at a particular time k. We are trying to forecast the load at a particular time k based on the load at k minus 1, 1 hour before, k minus 2, 2 hours before, k minus 3, 3 hours before, and k minus 24, that means 1 day before, k minus 48, that means 2 days before, and k minus 72, that means 3 days before. So actually I have a column data, but we have to process it to make it a input and output. My inputs are k minus 1, k minus 2, k minus 3, k minus 24, 48, and 72. These are the inputs, and this last column is called as the output. I have to rearrange the data. This column data I want to rearrange like this. For that purpose, I am writing this piece of code. So sorry, you have to run this cell. First, you have to initialize your A matrix. Then you have to run this cell. Now you have the data. Actually, this is the data as a column matrix. Now you have a data as a two-dimensional matrix. In this two-dimensional matrix, 1, 2, 3, 4, 5, 6. First 6 elements are the inputs, and last element is your output. Last element is your output. I think it's clear, right? Data computed. So now this is the data I want to use to train my ANN model. Okay. Now tell me, I want to split this data. Data is ready now. So first 6 are the inputs and last one is the output. Data is readily available with me. Right? Now tell me what the next step? Data. We have to split the data. To split the data, we have to use the train state split method. It split your original data A into training and also for the testing. I don't want to explain again because this part we already discussed. And again, forget about all the things. Now I want to explain about the back propagation algorithm, what we did for the. See, still now we discussed the code on some small data sets like this, but not on a real-time project or real-time application. This time I want to use the real-time application, the real-time project. So where the real-time project, where we get the real-time data, that is from the 33 by 11 kV substation. Okay. So I want to explain that part now. I don't want to go with, but this notebook is already shared with you. You can explore. You can explore. It will be more interesting for you because This is the last day. I don't want to, already we explained, drop learning explained, delta learning is explained, but with a small sample data, not in the real-time application. For the real-time application, I'm back propagation algorithm. I want to use this back propagation algorithm. So tell me, if anyone, why it is a weight matrix Wij. That means weight matrix between the input layer and hidden layer, and weight matrix between the hidden layer and output layer. Why it is a 6, 9, and why it is a 9, 1? Why it is a 6, 9, and why it is a 9, 1? Anyone, please. Here, if you observe these two lines, I will keep these two lines in my chart box. If someone responds, that will be more interesting for me. Why Wij 6, 9? Why Wjk 9, 1? Anyone, please? Anyone, please? Why Wij 6, 9? Why Wjk 9, 1? So Wij is 6, 9 because I have the 6 input features. The 6 input features are load on a substation 1 day before, 2 day before, sorry, 1 hour before, 2 hours before, and 3 hours before, 24 hours before. That means 1 day before, 2 day before, and 3 day before. Total 6 input features. That's why it is 6. And I took 9 neurons in the hidden layer. And I'm trying to predict only one output, that is load at a time k. Only one output, one prediction. That's what is the one. So random initialize. After that, as usual, same code. I have not used change the same code. Run this forward pass function, and also same code, but only changes the values, because Wij is the shape of 6, 9, and you have the 9 hidden neurons. That's why these values are changed. So based on your problem, the numbers will be changes. The numbers will be changes, right? So now run this backward pass. Now you can use the back propagation algorithm, which include the forward pass for the predictions and also backward pass for the weight updation. I'm taking the learning rate as a 0.001, and I want to run this algorithm for the 100 epochs. It may take some time because it is real-time data, which is contains 2100 112 for 2112 samples are there. So it will take more time. We will not get the output early that what we get previously in the previous exercises. Okay, then the training was completed. So these are the updated weights and the bias parameters. Now we, as usual, calculate the predictions with the test data and calculate the mean square error. So calculate the predictions. If you want to calculate the predictions, use the forward pass function. See, this forward pass function and backward pass function, we developed from the scratch using Python, not from the libraries. I'm not using the libraries. We are writing the every line by line based on the mathematics what we discussed. Okay. Similarly, this is the mean square error we are calculating. This is the actual values and these are the predicted values. Right. And let us assume. So my errors are 0.01865 something. So my error is almost close to 0. So then I'm stop this algorithm. I don't want to further train. If you are not happy, then you are retrain the model by changing the number of hidden neurons, by changing the learning rate, by changing the number of epochs, all the things we can do easily. Okay. So this is all about the back propagation algorithm for a load forecasting problem using the stochastic gradient descent optimizer. We are writing everything from the scratch. We are not using any library. We are writing everything from the scratch. Right? So we will take a break for the 15 minutes up to 3:15. And after that, we will discuss about the implementation of ANN with Keras. Now we will discuss about the Keras library for a regression problem. So when you are using the library, you don't bother about the you no need of more program. You require programming skills. You don't need, but you no need of extensive programming skills because everything is available in the form of library. So that we will discuss after a post session. So same, I want to work with the same load forecasting problem. Here I am writing my own code. We are discussing our own code from the scratch. But whereas here we will use the Keras library. Now we will use the Keras library. Okay, we will discuss about this one later. Okay, so this is from the session 1 of day 5. So small request is